The doubly symmetric fuselage section, shown in the figure below, has been idealized into an arrangement of direct stress carrying booms and shear stress carrying skin panels. All the boom areas are 150 millimeters squared. Calculate the direct stress in the booms and the shear flows in the panels when the section is subjected to a shear load of 50 kilonewtons and a bending moment of 100 kilonewton meters. So first, they give us a boom area to be 150 millimeters squared. They give us a shear force in the y direction of 50 kilonewtons, which can be converted to 3 newtons. And they also give us a direct stress. Let me highlight this. Shear load, bending moment. So they give us a bending moment of 100 kilonewton meters, which is in the x direction, or in the x-axis. So mx is equal to 100 kilonewton meters, which we have to convert to newtons and millimeters. So that will be 100 times 10 to the power of 6 Newton millimeters. We also know that due to the geometry being symmetric, we can say that boom 1 is equal to boom 6. They're the same distance away from the centroid, or the center axis, which is the x-axis in this case. So we can say that y1 is equal to negative y6 because it's below the x-axis. Same thing with boom 2 is symmetric with boom 10 and 5 and 7. So boom 2 is equal to 10 and negative 5 and negative 7. And same thing with 3. Distance from the center is the same as 9 and 8 and 4. So we can say that y3 is equal to y9, negative y of 4, negative y of 8. Let's solve for the direct stress first. So we know the formula for direct stress is this right here. We also know that there is no bending moment in the y-axis, and because of the geometry being symmetric, we know that a moment of inertia of xy is 0. So we can simplify this down to direct stress is equal to mx over ixx times y. Now, we know that this geometry is idealized. So the formula for an idealized moment of inertia is, this is the idealized moment of inertia formula for ixx. We also know that the boom area, all the boom areas are the same. So we can factor out the boom area, which will mean boom times the sum of y squared. So let's plug in what we got. Ixx is equal to boom area, which is 150 millimeters squared. Then we have to multiply by y. So let's solve for y. We know that the distance from 3 to the centroid is half of 500. So half of 500, which is 250. We also know that, let's do this one first. 1. The distance from 1 to the centroid is 250 plus the radius. So it's given here as 500, which is 250 plus 500, 750. All right, this one for boom distance of boom 2 from the centroid is, let's see, we know that from here to here is 250. So we have 250 plus, we know that this distance is 500. We need to find the green distance from here to here. We know that it also gives us the angle, which is 45 degrees. We can say that the radius sine of 45 will give us the distance on the green. So this will be 603.6. Let me write it down here. 1 is 750. 2, and all these are all equal to 603.6, and 3 to 50. Let's plug it in here. So we know that y1 is 750 squared. We also have to multiply by 2 because there's two booms. So we'll say times 2. And the sum of 603.6 squared times, there is 4 in this case, so times 4. And again, boom 3 is 250 squared times 4. And if we solve for this, IXX is equal to 4.25 times 10 to the power 8. Now we can plug in IXX to our direct stress bending moment due to bending moment formula. So we know that. Let's solve for 1 first. We know that mx is 100 times 10 to the power 6 Newton millimeters. 100 times 10 to the power 6 over IXX, which we found to be 4.25 times 10 to the power 8. And we also have to multiply by the distance from the centroid we're solving for 1 again. Distance, which will be 750. Alright, and if we solve that, that would be 176.5 Newton millimeters squared. So we found the direct stress in boom 1. And because of symmetry and what we wrote down here, we know that the direct stress of boom 6 is equal to the negative of boom 1, which is 176.5. Again, let's solve for boom of 2, direct stress in boom 2. Again, it's 100 times 10 to the power 6 over 4.25 times 10 to the power 8, and the distance away from the centroid axis, which is 603.6. And if we solve that, that'll be 142.02. And again, based off symmetry, we can say that 10, 5, and 7 are all the same. 10, 5, 7 are all the same, except for let me write this. 10 is equal to 6. Oh wait, 142.02, and then 5 is negative of 2, so 142.02, negative 142.02. Okay, now let's solve for the direct stress of boom 3. Again, the same thing, 100 times 10 to the power 6 over 4.25 times 10 to the power 8, multiplied by the distance from the center, which is 250. Solve that. 58.82. Again, we know that it's the same as 9 and negative for 4 and 8. So direct stress of 9 is the same as this, 58.82. 4 and 8 are the same, negative 0.82, but negative 8.82. That is the direct stress for all the booms. Now, let's solve for the shear flow. Again, we know this is an idealized geometry, so this is the formula for an idealized shear flow for an open section. We know they don't give us shear flow in the x direction, so we can say this is 0. And again, IXY is 0 due to symmetry. We can simplify all of this to be SY IXX times the sum of the boom times the y distance. Again, this is only for a open section. This is a closed geometry, so we know the formula for a shear flow for a closed section is just Q sub S QB plus Q S naught. And we know that QB is this one. We can just plug it in by adding that. QS is equal to SY over IXX times the sum of boom area times y distance plus QS naught. And that is the formula we're using. We can solve this. We know SY is given here as 50 kilonewtons. We converted to newtons, so 50 times 10 to the power 3. 50 times 10 to the power 3 over IXX, which is 4.25 times 10 to the power of 8. And again, we know that the boom are all constant, so we can factor that out. 150 times the sub of y plus QS naught. If we just solve for this, QS is equal to 10.018 times y plus QS naught. So first we have to make a cut in the geometry. Let's move all this down, plug in the geometry. So we're going to make a cut in between 8 and 9. This will be equal to 0. So if we write this down, let's move up here. Q of 8 to 9 is 0. And let's continue from there, from 9, and go all the way around. So we know that shear flow from 9 to 10 is equal to what we have here, the formula. So it's going to be negative 0.018 times the y distance, which of the boom that we passed. So from 9 to 8, 9 to 10, we passed 9. So 9 is 250 times 250. Let's also move this down so it'll be easier to see here. All right, 250. And that we also have to add the shear flow from the previous section, which in this case is Q89, and it's just 0. We don't really have to add anything, which will be, if we solve for this, will be 4.5. Again, shear flow from, we already did this. Shear flow from 9 to 10, we already figured out was negative 4.5. Now we need to find the shear flow from 10 to 1. So from 10 to 1 is equal to the formula that we have, 0.18 times the boom area that we passed, which is in this case, we passed 10, and 10 is 603.6. 603.6, and then we add the shear flow from the previous section, which is this negative 4.5, and again, we solve 15.36. All right, we got 1. So now we need to find the shear flow from 1 to 2. So from 1 to 2, which is negative 0.018, times the y distance of, we passed 1, boom 1, so 750, plus, again, the shear flow from the previous section, 15.36, and then we solve that to be negative 28.86. Again, shear flow from 2 to 3. So we already did from 8 to 9, 0. We made the cut there. 9 to 10, we found negative 4.5. 10 to 1 is negative 15.36. 1 to 2, and we need to find 2 to 3. So 2 to 3, again, the formula that we've solved, which is negative 0.018 times the boom distance from the centroid of the boom that we passed, which is, in this case, we passed 2. 2 is, again, 603.6 plus the shear flow from the previous section. And we can solve that to be negative 39.72. And now we need to solve for its shear flow from 3 to 2, or 3 to 4. Shear flow from 3 to 4, again, negative 0.018 times the distance to the centroid of the boom that we pass, which in this case is 3, and 3 is 250, plus shear flow from the previous section, 3.39.72, and we solve that to be negative 44.22. All right. So if we were to draw it here, we know that, so 8 to 9 is 0. 9 to 8 is negative 4.5. And there is no negative in the shear flow, so it just means it's going the opposite direction. So instead of going from 8 to 9, it's going from 10 to 9 in a positive 4.5 shear flow. And again, from 10 to 1, so it's negative, so it's 1 to 10, is 15.36. 2 to 1 is 28.86. And 3 to 2 is 39.72. And 4 to 3 is 44.22. And again, because the geometry is symmetric, we can say that shear flow of 9 to 10 is also equal to 8 to 7. So shear flow from 8 to 7. 10 to 1 is 7 to 6. So shear flow of 7 to 6. Then again, 1 to 2 is the same as 6 and 5. Shear flow of 6 to 5. And shear flow of 2 to 3 is 4 to 5. Or 5 to 4. And 3 to 4 is the same all the ways. So this is the shear flow, but we need to find the correction shear flow for all of them now. We solve for a geometry that is open, even though that this is a closed geometry. So what we need to do is solve for a shear flow of 8 to 9, because it's not equal to 0. So to solve for that, we need to use the moment equivalence equation, which is This is the equation for the moment equivalence equation. We can simplify Sx is equal to 0, and QB is a constant. So we can show that Sy is, we can simplify it to be QB ds plus 2 times the area of QS naught. And we also know that QB, this formula, is equal to the sum of QB times just 2 times the area. And again, simplify it, plus 2 times the area of QS naught. That is the final equation that we will be using to find the correction shear flow. Now, we need to find the area of each section. So, because it is symmetric, because it's doubly symmetric, we can say that we only had to solve the area for this part and say it's the same as this part, and all this is the same as this part. So, let's solve for the easiest section, which is from 3 to 4. We just need to solve for this. We know the area of a triangle is just 1/2 base times the height, which is 1/2 base, which is 500 times the height, 250. And we can solve that to be area of 3 to 4 is 62500. And now let's solve for the other section, which is 1 to 2. Let's solve 1 to 2 first. 1 to 2 first because it's a bit easier. Let's see. We could do the triangle of this, but we will be missing this little section of the area. So we can solve by doing, this is the center of the circle. We can solve this section first, and we can also add this section. So again, formula for a area of this circle, the little circled section here, is pi r squared times the angle, which is 45 over 360, and we add this section, which is 1/2 the absolute cross product of 0.0 cross product of 0.0, and to 0.0 is this point right here, which is x0 y 250. That is 0.0. 0.2 is the we know the y direction is 603, so 603.6. X direction we need to solve, which is 500 cosine 45. So 500 cosine of 45 is the x direction, which is equal to 353.6. And if we solve for that, which would be 0 to 50, x and y, 603.6, 0 times 603.6 minus 250 times 353.6, and that will be 88400. And if we solve for all of this, adding the pi r squared of 45 over 360, R in this case is 500. We can solve for this to be area of 1 to 2 is equal to 142,374.88. All right. Now we need to solve for area of 2 to 3, which we know, again, we can solve for the area of a semicircle, which is from point 0 to 2 and 3. But we also need this section right here. And we don't know this point, so let's try to find a different way. We know that this section right here is just a block. We just need to find this section. We know this is equal to what we found here. We can just subtract it on the other side of this side. So, or added, I meant. We added right here. So let me write down the formula that we have, which is, again, pi r squared of 45 over 360. We add the triangle, the area of a triangle, which is 62500. And now we need to subtract what we found here. Subtract all this, which is, again, what we found, 1/2 of 0.0 to 0.2, which is what we found here, and area 1 to 2, which is 188,400. And if we solve all this with our radius being 500, we know that the area of 2 to 3 is, we subtract this. And if we solve for that, we know that this is now equal to 116,474.8 millimeters squared. And that's the area that we found. We also know that we can, based on geometry, we can say that area 3,4 is the same as area 9,8. Based on geometry, we can say this and this are the same. This and this are the same. So area of 1 to 2 is the same as area of 10 to 1. And again, area that we found here of 2 to 3 is the same as 10 to 9. Area of 9 to 10, sorry about that. 9 to 10. Now we get our formula here that we have. Copy, paste. Let's put it right here. All right. We know that the SY, the shear flow that it was given to us to be all the way up here, 50 times 10 to the power 3 Newton millimeters or newtons. Again, we just need to apply it here. 50 times 10 to the power 3 times the distance. This right here is the distance. We can see it here. We have put that here, which is 250. Again, the sum of QB times 2 times the area, which is, hold on. Let's simplify the equation a little more. We know that, all right, so we can factor out a 2 since this is a sum. This is Q 3,4, 2 times area plus Q times 2 to 3, and 2 times area plus so on, so on. We can factor out a 2. That will be 2 times the sum of QB times the area. And we gotta add 2 times the area of QS0. So now that we factor out a 2, we also know that we only solved for this half of the geometry. So we need to multiply by 2 again to get the bottom half of the geometry, which will be multiplied by 2 again, which will mean that this is a formula that we are using. So let's bring this back up. And now we need to solve for Q times Q shear flow times the area. So shear flow of, let's see, 3 to 4 and all the way around. So shear flow of 3 to 4 is what we found here. Let's bring this down. All this down actually. Copy. Paste. So shear flow of 3 to 4 is negative 44.22. Negative 44.22. And multiply by the area of 3 to 4, which we found here to be this 62,500. Yes, 62,500. We add shear flow of 2 to 3, which is the next one here. Again, is negative 39.72, and the area of the area of 2 to 3 is this one, 116,000. 116,474.8. Add again shear flow of 1 to 2, which is negative 28.86 times area of 1 to 2, which is here 142,374.8. And then we add again, let's put it down here, shear flow from 10 to 9, which is negative 15.36, and 10 and area of 10 and 1 is the same thing, 142,374.8. Add again from 9 to 10 is negative 4.5 times the area of 9 to 10, which is again 116,474.8. And then we also have to add 0 for shear flow of 8 to 9, which is 0. 8 and 9, area of 8 and 9 is the same, it doesn't matter. And if we solve for this, it would be, this part will be 1, 2, 5, 5, 0, 0, 1, 2, 3. And this part would be 1.42 times 10 to the power 7. And we also, so all we did here was solve for this area, this part right here. Now we just need to multiply by 2 times. So multiply by 2 is equal to negative 2.84 times 10 to the power 7, and then multiply by 2 again. Multiply by 2 again, which will be equal to 5.68 times 10 to the power 7 plus, and again, we only saw for this section right here, we needed to add 2 times the total area times the correction shear flow. 2 times the total area times the correction shear flow. We need to solve the total area, so let me add the geometry here again. Let's see what we got. So we know that the total area is just the entire geometry. So this section is just base times height, which is 500 times 2, 1000 times height 500. We also need to add the semicircle up here, which is just base 1/2 pi r squared, 500 squared. And then we also need to multiply it by 2 because there is two semicircles. And that would, if we solve for that, that will be equal to the total area is equal to 1,285,398.2. We plug that in and we solve for the correction shear flow. So 125,00600 is equal to 5.68 times 10 to the power 7 plus 2 times 1,285,398.2 times QS naught. We solve for correction shear flow QS naught, which is equal to 26.97. Now, to find the actual shear flow, we need to add it back to shear flow that we solved before. Copy. Add it back, which means that this is now equal to, well, we need to add 26.97 all the way down, which means this is equal to 26.97, 8, 9, and 9 to 10 is equal to 22.47, 11.67, negative 1.89, negative 2.75, and then negative 17.25. That is the actual shear flow, the corrected shear flow. So if we were to draw it in our geometry again, so from 9 to 10, or 8 to 9, is 26.97. From 9 to 10 is 22.47. From 10 to 1 is 11.67. From 1 to 2 is negative, so just go the other way. From 2 to 1 actually is 1.89. From 2 to 3 is negative, so it goes the other way, 12.75. And then from 3 to 4 is negative, so it goes the other way as well, 17.25. And geometry, we can say that 8 to 7, it's the same thing, 22.47. 7 to 6, 11.67. 6 to 5 is negative, so it just goes the other way, 1.89. And 4 to 5, or 5 to 4 is negative the other way, 12.75. That's how the shear flow actually looks like. And that is all that is asked of us to solve.